Your turn.
Okay, I see. Okay, thank you, Martina, for the very nice introduction. And yes, indeed, now it's the midnight in China. But I think I have no choice. I have to give the talk. So first of all, welcome to this talk, and also Happy New Year of the Rabbit. This is the Chinese New Year. Sorry that I changed the title at the last day. So today we're going to talk about the land-ocean contrasts of trends in cloud amount under global warming. So as is shown by this true color image, clouds are essential part of our climate system. It covers more than 60% of the surface and play a critical role in the global water cycle. The distribution of clouds shapes the distribution of the fresh water supply and also our climate, such as the clear overlapping between the deserts and the nearly cloud-free regions, and also the tropical rainforests and the regions with frequent deep convections. Also, clouds play a critical role in the Earth's energy budget, the cloud radiative effects, CRE. So shown here in the bottom is the total absorption and scattering for cloud-free atmosphere. So as we can see, there are very low values over most of the visible radiation and some of the infrared radiations. This is indicate for the optical windows as well as the infrared window. These low values, meaning radiations with these wavelengths, will easily go through the cloud-free atmosphere. But with clouds, these windows are closed. So on one hand, clouds can reflect the incoming solar radiation and cool the system. Also, clouds can block the outgoing terrestrial radiation and warm the system. And by considering both of them, we get the net influence of clouds in the Earth's energy budget at a cooling rate of about 20 watt per square meter. But these values are not fixed and they could vary significantly, mainly depend on factors including the cloud properties such as the cloud amount, the cloud top temperature, and the cloud optical depths, as well as the conditions for the atmosphere and the covered surface. So in this talk, we focus on cloud amount because this variable gives, first of all, the fraction of our sky that is covered by clouds. And during the last century, our climate has been warmed up significantly. So shown here is the anomaly of annual global mean surface temperature. So as it's suggested, compared to the 1951 to 1980 average, the year of 2020 has been warmed up by more than 1 Celsius degree. And global models further suggest that such warming trend could appear only if we forcing the system with anthropogenic greenhouse gas emissions, especially the emission of carbon dioxide, the CO2. The greenhouse gases, such as the CO2, they could warm the climate because they have some absorptions over some of the major terrestrial radiations that is not closed by the other components of the atmosphere. However, even the CO2 is believed as the main driver of the shock warming. Its radiative effect is actually much weaker compared to the CREs. So for a doubling of carbon dioxide concentration in our atmosphere will cause a warming rate for the surface of about 3 watt per square meters, which is nearly 1 magnitude smaller compared to the value for the net CRE. Therefore, even small changes in cloud properties will potentially perturb the warming rate due to the increased CO2. And we use cloud feedback to quantify such potential influences of clouds in global warming. The cloud feedback is defined as the changes in CRE per unit change in global mean surface temperature. And the latest IPCC reported a positive cloud feedback with high confidence while the value of cloud feedback for a doubling of CO2 in our animal field is about 0.5 watt per square meter per Kelvin. This means changes in cloud properties will further speed up the warming due to the increased CO2, which is not a bad, not a good news. It's a bad news, but luckily, these predictions is mainly depend on a couple of global climate models and has large uncertainties. So shown here in the figure is the global mean feedbacks for global changes under global warming. And it's clear compared to the other components, the cloud feedback offers the greatest uncertainty. A further decomposition of the cloud feedback into different cloud properties further suggests that changes in cloud amount dominate the uncertainty in cloud feedback, which means assessing the trend in cloud amount that associated with global warming is extremely important. The cloud feedback is very hard to estimate because clouds are complex. So they could vary with very different scales. The spatial scales of clouds could vary from hundreds of meters to thousands of kilometers, with the corresponding temporal scales could vary from minutes to days. Also, more importantly, even for cloud systems that have the similar spatial temporal scales, they could have very different organizations, which is shown by these subplots. And this is especially true for the stratocumulus over the subtropical eastern oceans. That is identified as the most efficient cooler of our system. So these complexities challenges both the physical understanding of the cloud processes as well as the representation of clouds in current climate models. With a typical horizontal resolution of tens of kilometers and a typical time step of tens of minutes, current climate models can describe the clouds only if we based on the parameterization schemes, and therefore they show large uncertainties. Also, the global warming is complex. Apart from the forcing from greenhouse gas emissions, perturbations such as the volcanic eruption and some other nature variabilities, as well as some regional feedbacks, also play a critical role in the climate system. Therefore, they leading to a non-linear global warming trend, as well as an inhomogeneous 2D warming pattern. So to get the response of clouds to global warming correctly, we need a good data and also the right method that is able to decompose the warming related processes from other climate perturbations. So here in our work, we perform the empirical orthogonal function, the EOF analysis on data from ARA5. We use EOF analysis because it can decompose a given spatial temporal field into a set of modes that is independent. And all of these modes may link to physics and dynamics of the checked domain. And also the EOFs is widely used in meteorology, but not so much in the cloud field. The revealed EOF modes were further ordered by the explained variations. It gives a measure of the dominance of the mode in the total variance of the data, with leading modes with higher explained variations indicate for major physical processes that controls the system. And more specifically, for each EOF mode, it gives the anomalies in the spatial domain. And it has a principal component, the PC, that gives the variations in the time domain. Arrow5 is the 5th generation of atmosphere analysis data from ECMWF. Its model output, but is constrained by observations that is with strictly quality control. So we choose Arrow5 here because it offers us uniformly sampled long-term data. And also Arrow5 is validated as the most reliable real analysis data set for climate trend assessment. Also, data from Arrow5 actually agrees very well with the state-of-the-art observations, which we will talk later. The variables used in this work include the skin temperature, ST, the total cloud cover, TCC, as well as the relative humidity, RH, and some other variables. All of the variables used is the monthly data during the period of 1997 to 2020, with a horizontal resolution of 0.25 degree. So here we firstly checked the climatology of the skin temperature, which is the map shown here. So as expected, this map gives nearly uniform gradients from equator to the poles. Shown in the right, we also checked the annual global means of skin temperature, which is the red curve. Overlapped on this figure, we give the global concentration of CO2, which is the black curve. And also we highlighted some nature variabilities above. And as it's shown, the annual global mean ST increase very nicely together with the CO2 concentration. Also, it captures very nicely the long-term warming trend as well as the short-term climate variabilities. Here we give the same results, but for the total cloud cover. So again, the climatology gives kind of expected patterns for the cloud amount. So for example, the high cloud amount over the tropics, the subtropical eastern oceans, as well as the mid to high latitudes, and also the low cloud amount over the deserts and the subtropical western oceans. But there is no consistent trend captured by its annual global means. Instead, we see very significant interannual variabilities and relatively short-term variations, meaning climate perturbations rather than global warming dominated the variation of the global cloud amount during this studied period. Therefore, we next perform the EOF analysis on this data to reveal the potential drivers of these variations. Here we give the leading EOF and the leading PC for the skin temperature. So as already introduced before, the EOF mode gives the anomaly in the spatial domain, while the PC gives the variations in the time domain. In other words, for a given region, the time variations captured by the PC is depicted, its direction and its magnitude is depicted by the value of the EOF. So for this mode in the skin temperature, it accounts about 30% of the total variance, and its EOF gives a nearly worldwide distribution of positive anomalies together with a very significant increase in trend, meaning this mode captures a nearly worldwide warming trend. And more interestingly, the PC, the leading PC, which is the blue and red bars, change together with the annual global mean ST, which is the black curve, almost perfectly, meaning this mode is mainly associated with global warming. Also, if we take a closer look at its EOF, it's also give kind of regional patterns that is known for global warming, such as the most significant warming trend over the Arctic, as well as the nearly double warming rate over the land compared to the oceans. also some kind of weak warming or even cooling signal over part of the North Atlantic, the Southeast Pacific, and the Southern Ocean. After that warming-related mode in skin temperature, the second EOF in skin temperature accounts for about 10% of the total variance, and with a much more complex distribution of positive and negative anomalies. Also, its PC shows very significant inter-annual variabilities. So the black curve shown in the PC2 here is the Oceanic Nino Index, the ONI. So ONI is a measure of ENSO with large positive values for El Nino years and large positive values for La Nina years. And as it's shown, the PC2 correlate very strongly with the ONI, meaning this mode is mainly driven by ENSO. And also, as expected, the EOF mode gives the spatial patterns that is consistent with the known patterns for ENSO-related temperature anomaly, such as the unusual warming over the Central and Eastern Tropical Pacific for El Nino years and cooling for La Nina years. And beyond the Pacific, we also see consistent and significant anomalies worldwide. This suggests ENSO as an essential part of the global climate. And these revealed patterns and variabilities is not brand new, but it offers very good validations that support the skin temperature in Arrow 5 is a very good proxy of the recent climate variabilities. Also, it validates the good performance of the EOF analysis in decoupling the warming-related processes. And based on these results, then we go to the results for the total cloud cover. Here is the leading EOF and the PC for the total cloud cover. So again, shown in the left is the EOF1, and it accounts for about 20% of the total variance. And shown in the right is the PC1 and the ONI. Again, the PC1 and the ONI shows close correlations, meaning this EOF mode captures mainly the influences of ENSO in cloud amount. And its spatial patterns is also as expected. For example, during El Nino years, it suggests increased cloud amount over the Central and Eastern Tropical Pacific, decreased cloud amount over the Western Pacific. These patterns and variability agrees well with previous observations and simulations, but just to offer an easier comparison between the total cloud cover from Arrow 5 and the satellite observations of real cloud amount, here we mimic the EOF analysis, but for data from satellite observations. So the data used for these figures is daily averaged cloud fraction from MODIS about Agua during the period of 2002 to 2021 with a horizontal resolution of 1 degree. And just similar to the results shown for the total cloud cover from Arrow 5, this leading mode of observed cloud amount accounts about 20% of the total variance and give very similar distribution of positive and negative anomalies, as well as close correlation between its PC and the ONI. So these results suggest that even though the total cloud cover from Arrow 5 is mainly model output, it's a diagnostic variable that is notched to some observed meteorological conditions, but the total cloud cover do captures the spatial temporal variations of the real cloud amount. And very interestingly, after decouple such ENSO-associated mode in cloud amount, the following mode of the total cloud cover gives a PC with a very significant increase in trend. And this PC changed together with the annual global mean ST with a correlation coefficient of about 0.8. These correlations between the PC and the annual global mean ST suggest this EOF mode as the influence of recent warming in total cloud cover. So the distribution of these anomalies is complex, but the most distinct feature is the land-ocean contrast. So generally speaking, we got a very consistent decrease in trend over the continents, where a general increase in trend over the oceans, especially over the tropics and the subtropical eastern oceans. So these land-ocean contrast could have very important implications. So optimistically, the increasing trend over the eastern subtropics may imply a possible negative cloud feedback, since we have large stratocumulus decks here. And very worryingly, the decreased cloud trends over most of the lands may suggest additional warming, and which is already twice faster warmed up than the ocean, and potential stress on freshwater supply. In particular, the decrease in trend of cloud amount over the Amazon, the Congo basins is not good news to hear. And moreover, such land-ocean contrast may indicate for the changes in the energy partition over the land and over the ocean. Therefore, they may further cause feedbacks as well as changes in the general circulation. So before giving more analysis, we stop for now and consider the issue of the signal leakage in EOF analysis. So unlike the EOF modes, physical processes are not necessarily orthogonal. The variations caused by one physical processes could split into different EOF modes. Also, the variations caused by different physical processes could contribute to the same EOF, which is known as the signal leakage. And in our case, significant signal leakage may produce incomplete modes, and therefore need to be, first of all, validated. So the easiest way to check this issue is to check the variances and the correlations between all the EOFs and the PCs, because EOF modes affected by significant signal leakage issue is expected to have similar explained variations as well as similar features in its EOFs and PCs. Given here is the results for skin temperature, the top panels, and the total cover, the bottom panels. We give the explained variations for all of the modes, as well as the correlations for between the top two EOFs and the top two PCs with all other EOF modes and other PCs. So as it's shown, no matter for the skin temperature or for the total cloud cover, the top two modes that is discussed in our previous slides showed much larger explained variations compared to all other modes. Meanwhile, they show relatively weak correlations with all other modes, meaning the signal leakage issue is not a significant issue in the modes that we already discussed. And also, please note that we use the Spearman's rule to measure the correlations, because this is a parametric statistic and with no assumptions in the distributions of the samples. Another benefit of the reanalysis data is, as model output, the variations in this data is more explainable. So to take this advantage, and here we checked the thermodynamic drivers for variations of total cloud cover. To do so, we assess the correlations of total cloud cover and each meteorological variable, including the relative humidity, the specific humidity, the temperature, the vertical velocity, the U wind component, V wind component, the wind divergence, the potential vorticity, as well as the relative vorticity at 23 pressure levels, ranging from 1,000 hectopascal to 200 hectopascal. The figure shown here is the averaged correlation over the land, the red curve, and the ocean, the blue curve. So it's clear that RH in most pressure levels yields the strongest correlation with the continent TCC. While RH and specific humidity yield comparable strong correlations with the maritime cloud amount. So to better understand such correlations, we shown here the map of the meteorological variable group that has the strongest correlation with total cloud cover. So what we do here, first of all, we calculate the correlations between total cloud cover and each meteorological variable per pixel. And then we mark the pixel by the color of the variable that gives the strongest correlation. And very interestingly, over nearly all of the continents, we see the dominant role of relative humidity in variation, in controlling the variation of total cloud cover. Meanwhile, over the oceans, we see much more significant regional dependencies of its main driver. For example, the relative humidity and specific humidity over parts of the low latitudes, and also the potential vorticity over mainly the mid to high latitudes, as well as the Arctic. But such contrast between the main driver of the cloud cover is consistent with the different atmospheric condition over land and over ocean, and also the different dynamics of continental clouds as well as the maritime clouds. And another thing we would like to highlight here is such dominant role of relative humidity for continental cloud amount is kind of unique. So shown here is the same results, but for the second strongest correlation, meaning the best strongest correlation we showed before is removed from these results. And as it's shown, we see after relative humidity, there is no other single variable that dominates the variations of cloud amount over all continents. Instead, this map gives us kind of noisy-like distribution of the dominant factors for variations in cloud amount. And go back to the average correlations over land and over ocean. We see here the low level relative humidity gives a global peak over the land and a local peak over the ocean with the values of 0.65 and 0.43 respectively. So this global peak over the continental clouds suggests that the variations in continental cloud amount is firstly determined by the humidity perturbations just slightly above the surface. And this is consistent with the Potho theory for convective clouds, which suggests that low-level relative humidity will determine the likelihood of the cloud formation and as well as its extent. Also, the low-level relative humidity represents a more localized processes by considering the high-level relative humidity may affected by processes such as the cloud evaporation and the long-distance water vapor transport. So, to further explore the thermodynamic driver of the continental clouds, here we introduce the near surface relative humidity. The we define the near surface relative humidity as relative humidity at a pressure level of 50 hectopascal above the local surface to take into account the terrestrial topography. The map shown here gives the correlation between the near surface relative humidity and the total cloud cover. And again, we see distinct land-ocean contrasts. Over lands, we see nearly 1-to-1 correlations over between near surface relative humidity and the total cloud cover. But over oceans, this is not the case. We see much weaker correlations. And these results suggest that the near surface relative humidity is the most plausible explanation for the changes in total cloud cover. And also, I would like to see that the average correlation between the near surface relative humidity and total cloud cover yield an average value of about 0.69, which is higher than all of the higher than the values over all of the standard pressure levels. And here is the linear trend in near surface relative humidity. Again, it shows consistent decrease in trend over most of the continents, but not over the oceans. And this is quite reasonable, but considering the much more limited water source over land, and as well as the much quick warming over the land than over the ocean. And by compare these distributions of the linear trend in near surface relative humidity to the warming associated mode in the total cloud cover, we see they show similar spatial patterns over the land, but not over the ocean. And all of these results suggest that the reduction in near surface relative humidity is the most plausible explanation for the decreased continental cloud amount, but not the changes in the maritime clouds. And here comes the conclusion. So this is the take-home message. EOF analysis on R5 data over 1979 to 2020 reveals a trend and an ENSO-like mode in surface temperature and cloud amount. And the trend-like modes are most likely associated with global warming. The trend-like mode in cloud amount shows clear land-ocean contrasts with a general decrease in trend over the land and a general increase in trend over the oceans. Also, we checked the meteorological drivers for such changes, and we see the meteorological variable that dominate the variation of cloud amount is different over land and oceans. And also, we propose the reduction in near surface relative humidity as the most plausible explanation for the decreased continental cloud amount. And thank you very much for your time. This work is currently available on the ACPD, so you can scan this QR code. And also I give our emails. So questions and suggestions are welcomed by any means. And thank you again.